Hello guys, welcome to PDV Lidex Education. This is another moment when we are going to discuss some important things. So here we are going to do some chemistry. I have some series of exercises which have been sent to me from a secret source. By a secret source, and these exercises are believed to be a sample of Cameroon GCE this academic year. Cameroon GCE this academic year. So whether you are in lower seat, whether you're in upper seat, please get seated and let's answer these exercises together. Yes, there's physical, there's inorganic, and there's organic. So as I said, the exercises are from a secret source. Okay guys, okay. So please, as you all know, you are going to enjoy the lesson, right? For that one, I know you are already assured that the lesson will be good. So please kindly like the video, press the share button, share the video before you even consume it yourself. So please share the video, press the share button and repost the video. We shall be very grateful when you do that. So thank you so much, and get seated and let's do this together. Okay, so the first question, the questions are in my phone. As I said, they are from a secret source, so we shall answer them together. So it starts like this. It says question 1 is on physical and general chemistry. This question is on oxidation number. Yes, Roman 1, define oxidation number. Define oxidation number. So as we all know, now before we define oxidation number, let's look at what oxidation numbers are. Right, we know that sodium, right, sodium when in a compound has an oxidation number of +1, right? And sodium, when sodium is in the uncombined state, its oxidation number is 0. Oxygen has an oxidation number. Oxygen has oxidation number of -2 generally, right? But in peroxide, oxygen is -1, while in the uncombined state, oxygen is 0. Right? Chlorine has an oxidation number. Chlorine has oxidation number of -1, right, when in a compound or an ion, while in the uncombined state, oxidation number of chlorine is 0, right, and so on. So what now is oxidation number? Oxidation number simply are these values that we have made here. We call them oxidation number. So how do you define oxidation number? Take care. While I was writing these numbers, I said two things. These ones are the values, right? These ones, they are the values when the element is either in a compound or an ion, right? When the element is either in a compound or an ion. But the zero, what are they? The 0 are the values. They are the oxidation number of these elements when they are neutral, when they are in the uncombined states, when they have not reacted, when they are they are neutral. Their oxidation number is 0. So what then is oxidation number? Oxidation number is defined as a positive or a negative number. A positive or a negative number assigned to an element in the uncombined state, or in a compound, or in an ion by the application of certain rules. Similarly, magnesium has oxidation number of +2 when magnesium is in a compound or an ion, but its oxidation number is 0 when magnesium is in the uncombined state, right? So once again, oxidation number is either a positive or a negative number assigned to what? To an element either in the uncombined state or in a compound or in an ion by what? By the application of certain rules. What therefore are those rules? What are those rules? Right? That's the definition. Now, what are those rules? The first rule is that the oxidation number of all elements in the uncombined state is 0. That's the first rule. The oxidation number of all elements in the uncombined state is 0. Second rule, metal ions have positive oxidation number. Next rule, non-metal ions have negative oxidation number. Oxygen has oxidation number of -2, except in peroxide, where its oxidation number is -1. For example, hydrogen peroxide, right? Here, oxygen is -1, right? Now, hydrogen has oxidation number of +1, except in metal hydride. For example, sodium hydride. Here, hydrogen is -1. Hydrogen has oxidation number of +1, except in metal hydride, where it is -1, and so on. Those are the different rules that we talk about. So once again, oxidation number is a positive or a negative number assigned to an element in the uncombined state or in a compound or in an ion by what? By the application of certain rules. Okay, let's go ahead. Next question says that it says calculate the oxidation number of manganese in permanganate, right? Oxidation number of manganese in permanganate. So we have manganese in permanganate. Oxidation number. As we know, we let the oxidation number of manganese to be X. And we know that the sum of all oxidation numbers in an ion must be equal to the charge of the ion. The sum of all oxidation numbers in an ion must be equal to the charge of the ion. And if it's a compound, a neutral compound, then the sum of all oxidation numbers is equal to what? 0. So if manganese is X, then we shall say that X plus oxygen here is -2. So we say 4 times -2. 4 times -2 equals to what? Equals to -1. So what is X? X is -1 plus 8. So X is +7. So manganese in permanganate is +7. Next question. We are asked to find oxidation number of nitrogen in nitrite. Nitrogen in the nitrite ion, like that. Yes. So again, we let nitrogen to be X, right? Oxygen is -2 except in peroxide. This one is not a peroxide. So nitrogen is X. X plus 2 into -2. 2 into -2 equals to what? -1. So X is -1 plus 4 plus 4. X is +3. So nitrogen in the nitrite ion there is +3. Next, oxidation number of sulfur in sodium thiosulfate, right? Sulfur in sodium thiosulfate. Sodium thiosulfate is N2S2O3. We are asked to solve for sulfur. Sodium is +1, so we say 2 into +1 plus sulfur is X, so 2X plus oxygen is -2, and there are 3 atoms, equals to what? The thiosulfate is a neutral molecule, so equal to 0. So what do we have? 2 plus 2x minus 6 equals to 0. 2x minus 4 equals to 0. X equals to +2. So sulfur in thiosulfate is +2. The next question, we continue. The next question says that oxidation and reduction are used in balancing equations of redox reactions. Oxidation numbers are used in balancing equations of redox reactions. Given the redox reaction below, right, we are given this reaction. We have iron 2 plus aqueous plus dichromate aqueous gives us iron 3 plus aqueous plus chromium 3 plus aqueous. Okay, write down, they say write the half equation for the reduction. Write the half equation for the reduction, right? So as we notice, iron 2 is oxidized to iron 3. Iron leaves from +2 to +3. Increase in oxidation number is called oxidation. So iron 2 has been oxidized by what? The dichromate, right? Acidified potassium dichromate. So iron 2 here is the reductant, right? Because the reductant has been oxidized. The dichromate is the oxidant or the oxidizing agent. Yes. So we are asked to write the half equation for reduction, right? The half equation for reduction. For reduction. So what has been reduced? Dichromate has been reduced to what? Chromium 3. So we write dichromate aqueous plus, we have to balance the equation. As we know, dichromate will be converted to chromium 3 plus aqueous. Now we balance, right? We balance the equation. Chromium here is 2, chromium here is 1, so we put 2, right? Now dichromate works more in acid medium, so we are going to add acid. We are going to add H plus because dichromate is a powerful oxidant in acid medium. It's more aggressive in acid medium, so we have H plus. Now the H plus is going to be oxidized in the process to produce water. So here we are going to have water liquid. We balance the equation. Oxygen here is 7, oxygen is 1, so here we put 7 like that. Hydrogen is 14, hydrogen is 1, so here we add 14 like that. We now balance the charge. Overall charge here, -2. -2 plus 14 is +12. Overall charge here, 2 times +3 is +6. From +12 to +6, how do we balance it? We have to add 6 electrons, right? We add 6 electrons because 12 minus 6 will give us +6. So right now we have the balance reduction equation of dichromate. Now we should also write the oxidation equation. We are also asked to write the oxidation equation. So what is oxidized? Iron 2 is oxidized to iron 3. So we have iron 2 aqueous, right? It is oxidized to iron 3 aqueous by what? By the loss of 1 electron, right? By the loss of 1 electron. Here we have +2 +3. To balance it, we add 1 electron here. +3 minus 1 will give us +2. So those are the half equations for oxidation and reduction. Now the next question says that balance the redox equation, right? Write the balanced redox equation. So to balance it, as we know, we are just going to add these two, right? We add so as to eliminate the electrons. Here there are 6 electrons, here there is 1. So we multiply here by 6 and we add. So we shall have the balanced equation as dichromate aqueous plus 6 iron 2 plus aqueous plus 14 H plus aqueous gives us 2 chromium 3 plus aqueous plus 7 water liquid plus 6 iron 3 plus aqueous. That is the balanced redox equation. Now if they ask us what is the color change in this redox equation, color change, here you must know that dichromate has an orange color. Dichromate has an orange color, while chromium 3 has a green color in solution. Dichromate solution is orange, while chromium 3 is green. So what's the color change? What do you observe in the process? What we observe is that the orange color, the orange dichromate solution is converted to what? A green solution. Orange dichromate solution becomes green. Why does it become green? Because dichromate is reduced to chromium 3 by what? By the iron 2 solution. Next question. If 25 cm cube of 0.05 molar potassium dichromate were required to react with 50 cm cube of acidified iron 2 solution, find the molarity of the iron 2 solution. Okay, we are asked to find the molarity, right? The molarity of the iron 2. Iron 2 is what? The reductant. So we apply mole ratio. So we have molarity of oxidant, volume of oxidant, all over molarity of reductant, volume of reductant is mole ratio of oxidant. The oxidant, the dichromate, right, the mole ratio is 1, while the reductant, the iron 2, the mole number is 6, so equals to 1 on 6. And we are asked to find the molarity of the iron 2, so the molarity of the reductant. Molarity of reductant is equal to, right, we cross multiply there and send 6. 6 times molarity of oxidant, volume of oxidant, all over volume of reductant. Right, we put the values, we substitute. So there we have molarity of reductant equal to molarity of reductant equals to 6 into molarity of oxidant. They gave us in the question, it is 0.05. 0.05. Volume of oxidant, they told us, right, 25 cm cube, all over volume of reductant was required to react with 50 cm cube of acidified iron 2. So volume of reductant is 50. So you substitute and you have your answer in molar, right? So you punch. That will be the molarity of the iron 2 solution. Okay. The next question goes ahead, right? So the next question goes ahead, and we are going to, right? Well, let's just answer the next question rapidly, right? So that we can finish the first part. So the next question says that when 21.6 cm cube of 0.18 molar sulfuric acid neutralizes sodium hydroxide solution, 0.30 gram of salt, sodium sulfate, was obtained after evaporation and weighing. Determine Roman 1, the molarity of the sodium hydroxide solution. So here we are reacting an alkali with an acid, right? So the first thing, we write the balance equation for the reaction. The first thing is that, so we are in part C. Balance equation first. Sodium hydroxide aqueous reacts with hydrochloric acid aqueous. Reacts with sulfuric acid. To produce what? To produce sodium sulfate aqueous and water liquid. Like that, we balance the equation. Sodium is 2, we put 2 here, right? Hydrogen, 2 plus 2, 4. Here is 2, so we put 2 here. That is the balanced redox acid-base reaction. We should find the molarity of sodium hydroxide. molarity of sodium hydroxide. So we have molarity of acid, volume of acid on, molarity of base, volume of base. Acid number 1, base number 2. You want molarity of base. Molarity of the base. Molarity of the base equals 2 times molarity of acid, volume of acid on volume of base. 2 times molarity of acid is given to us. It is molarity of the acid is 0.18. 0.18. Volume of acid is 21.6. All over molarity volume of base. Volume of base in the question is they say that 21.6 cm of sulfuric acid neutralizes sodium hydroxide solution. Volume of base was not given in the question, right? But this question came from GCE 2022, and there the volume of the base, right, normally it should be 25. It should be 25 because it is acid-base titration. One component has to come from the burette, right? And since the acid gives us a decimal volume, that means that the acid was in the burette, while the base was collected using the pipette. And as we know, the pipette used generally is a 25 cm3 pipette. So volume of base will be 25, right? It will be 25. So I believe that maybe they left it out for you to know that the volume will be 25. So when you punch that, your answer will give you 0.31 molar. Alright, that's the molarity of the base. Next question says that calculate the mass of sodium sulfate expected. What is the mass of sodium sulfate expected? So there we are solving for the expected mass. We're told in the question that after weighing, the mass obtained was 0.30 gram. After weighing, the mass obtained was that. We call this one the actual yield. And we are now asked to find the theoretical yield. So to get the mass of the salt, we use mole ratio between the salt and the acid, since they give us all the values of the acid. From the balance equation, what do we see? This is Roman 1, Roman 2. From the balance equation, the number of moles of the salt is equal to the number of moles of the acid, right? 1, 1, 1, 1. So therefore, a number of moles of acid is what? Molarity of acid, volume of acid. When you punch, molarity of acid is 0.18. Volume of acid in cm cube, 0.0216. When you punch that, you are going to have 3.89 times 10 to the minus 3 mole. That's the number of moles of the salt that were formed. Now what do we know? Number of moles of salt is equal to what? Mass of salt all over molar mass. So the mass of the salt is the number of moles of the salt times its molar mass. Number of moles of salt, 3.89. This answer, 3.89, 10 to the minus 3. Molar mass of the salt is sodium sulfate. Sodium, 23 times 2, you will make 46. Sulfur is 32. Oxygen, 16 times 4 will make us 64. When you punch that, it's going to give you 0.55 gram. That is the mass of the salt that was expected. Now, Roman 3, calculate the theoretical yield, right? Yes, let's find the percentage yield, sorry. This one is the actual yield, the mass that was obtained after weighing and evaporation. This one is the actual yield, sorry, the theoretical yield. And we are asked to find the percentage yield. Percentage yield, right, is equal to what? Actual yield all over theoretical yield times 100 on 1. Actual yield 0.30. Theoretical yield 0.55 times 100 on 1. When you punch that, you are going to have 54.5%. That is the percentage yield. The next question says that, next question, give one reason why the percentage yield for most reactions is never equal to 100%. Give one reason why percentage yield for most reactions is never equals to 100%. So there are many reasons for that, right? There are many reasons. The first reason is incomplete reaction, right? Reasons for low percentage yield. The first reason is incomplete reaction. Incomplete reaction. That means that most reactions don't go to completion, right? Most reactions don't go to completion, and as a result, they expect the actual value of product obtained is less than the theoretical value, because the theoretical yield assumes that all the reactants have reacted, but the actual yield is what we get in reality, right? The theoretical yield assumes that all the acid reacted. But as we are saying, the first reason why the percentage yield of most reactions is less than 100%, the first reason is due to incomplete reactions in which all the reactants don't go into reaction. That's the first reason. Incomplete reaction in which all reactants don't go into reaction. The next reason for low percentage yield is loss of product during recovery or purification. So there is loss of product during purification. Right? For example, in this reaction, we have to what? At the end of the acid-base reaction, we need to evaporate to dryness and weigh. We need to evaporate what? The final solution to dryness before we weigh the mass of the salt. In that process, right, some solution may spill off. Yes, some solution may spill off, or we may find ourselves losing some of the salt, and at the end of the day, what we measure is less than what was actually formed. So the second reason for low percentage yield is that there is loss of some product during purification or during recovery, right? In the process where you purify the salt before you measure its actual mass, right, some of the solution may spill to the floor, may spill on the onto the floor, and as a result, what you will measure will be less than what was actually produced. Then the next reason for low percentage yield is presence of impurities. Presence of impurities in the reactants. Right? Reactants react to give products. If reactants have impurities, those impurities can go in reaction, and as a result, they will influence the actual reaction that we expect. So the presence of impurities in reactants can also bring about side reactions, or can also influence the actual yield of the reaction. Because when you are solving for theoretical yield, you assume that the reactants reacted completely. So you ignore the fact that there could be incomplete reaction. You ignore the fact that some product could be lost during measurement or during purification, right, and measurement. You ignore the fact that the reactant that you have used may have been contaminated or may have impurities that influence the degree or the products from the actual reaction. And the last reason is what we call side reactions. Side reactions, right? Side reactions or unwanted reactions. Leading to the formation of what? Of unwanted products. So that's the next reason. Side or unwanted reaction. That means that in the actual reaction, right, as we mix the reactants, apart from the actual reaction that we expect, some other reactions may occur, and because they occur, they will use up some of our reactants. At the end of the day, we shall not have the actual quantity of product that we actually want. We call that one side reactions or side effects, side reactions or unwanted reactions. Those reactions take place within the actual what? The actual reaction mixture, and as a result, they use up some of the reactants, making that the amount of reactant that effectively react to give us the final product is what? Is lower than we had introduced. For example, I may put in 5 grams of sodium hydroxide, right? I may put in 5 grams. By the end of the day, due to side reactions, I may have only 4.3 grams that actually react in my expected reaction. At the end of the day, I have 0.7 grams that has gone into other reaction that I was not expecting to take place. So when you find percentage yield, you ignore all these factors, and as a result, your percentage will always be less than 100%. Okay, that one brings us to the end of this first session, right? We shall take a break now and come after to complete the inorganic and the organic sections. Thank you so much. Please like and share the video. God bless you.